Okay, well, we concluded then that our delta PE, change in potential energy, being equal and opposite to the work done on the system by the conservative force, is the negative of the negative 1/2 kx squared that we get here, or 1/2 kx squared. And I didn't write it down. This is a potential energy at position x relative to equilibrium, the potential energy relative to equilibrium at position x. That would have been a better way to write it, but I'm not going to rewrite it. Then I ask, okay, what's the potential energy if x is 15 centimeters? So you're 15 centimeters away from equilibrium, what's your potential energy? Well, that's really easy. Everybody just substituted 15 centimeters in here. Some people were careful with their units, some people weren't. You know, I didn't write it on the board because everybody had it in their paper, but K is 120 newtons per meter. Meaning that every meter you stretch this rubber band out, you get 120 newtons of force. Now, the rubber band would break before you stretched it a meter, but within the distances or the lengths of the rubber band that applied here, we're assuming that K was this. And remember also, you know, the force exerted by the rubber band was not perfectly linear. It wasn't even particularly constant. It wasn't conservative. But it was close enough that this model is still very useful. Okay, and of course, if you have a better, say a really good spring, a really good light spring, you get very close to the ideal behavior that we're analyzing here. Okay, well, anyhow, if you plug 15 centimeters in here and use this K and do 1/2 kx squared and be careful with your units, you find that the energy at that point, this expression, which is now the potential energy at position x, is 1.35 joules. Okay, now I did a little different analysis here because I want you to see this thing in two different ways, and then I want you to think about why they're the same. It's not real deep, but it's deeper than you're used to thinking, and I'm trying to get you to think a little more deeply whenever possible about situations rather than just pulling formulas off the shelf, applying them, and hoping they were the right ones. Okay. My reasoning is, at x equals 15 centimeters, your net force is negative 18 newtons. Just take 0.15 meters and multiply it by 120 newtons per meter, and you get 18 newtons. And of course, the net force is negative kx, so that would be negative 18 newtons. Okay, your net force then, as you go from equilibrium to the 15 centimeter position, net force goes from 0 to negative 18 newtons. And it does so linearly because negative kx is clearly a linear function. A graph of force versus position would be a perfectly straight line. Again, talking about the ideal case. So, that means that the average net force is the average between what you have here and what you have here, for any interval. For this interval, we're talking about from equilibrium out to position 15 centimeters, so the force goes from 0 to negative 18 newtons, and the average of that is negative 9 newtons. So that the work done by the conservative force on the system is the negative 9 newtons exerted by the conservative force, negative kx, times your 0.15 meters, that's negative 1.35 joules, and potential energy being equal and opposite to the work done on the system by the conservative force is plus 1.35 joules. So the potential energy is 1.35 joules at the x equals 15 centimeter position. Okay, you get that by this reasoning, which is very straightforward, very easy to understand, and very easy to do in your head. You don't have to square anything. And of course you get it from the formula. You can use the reasoning, you can use the formula, and you should be able to do it interchangeably, whatever's more convenient in a situation. And you should also be thinking about these situations. If the numbers are simple enough, you should be doing this in your head. You shouldn't automatically go to a calculator, because then you get no sense of the numbers, you get no sense of the magnitudes of things, and you end up not thinking about much of anything. You just end up getting results out of a black box that you hope are right. Okay, and I don't think that's a good idea to do physics or engineering. Somebody wants to disagree with me on that, especially somebody that really knows. I've got plenty of ex-students. Some of them would agree, some of them wouldn't. So take it with a grain of salt, but consider it. Okay, so anyhow, you got your potential energy relative to equilibrium at the 15 centimeter position.